Welcome back. Today's lecture, it's about transmission line performance. During this session, under the transmission line performance, we are going to analyze the circuit and obtain the ABCD parameters of a two-port circuit. Our work will cover the single phase, the balanced three-phase system, performance under steady state conditions. So, before we start our topic, let us recall our previous lecture. In our previous lecture, we discussed the parameters of a transmission line. Let's write down what we spoke about. We spoke about a resistance, we spoke about an inductance, we spoke about capacitance and conductance. That's what we spoke about during last lecture. Okay, today we are going to, during this series of lectures under the banner of transmission line performance, we are going to study the system characteristic or the circuit analysis characteristics of number one, a short line. Medium line. Long line. And lossless line. And a lossless line. Now, for a small line, like I said in a previous lecture, depending on the voltage, depending on the standard that you follow, this varies between 0 to 80 kilometers in length. And then the medium line, depending on the book, depending on the standard, but vary between 80, 160, or 250. In our book, this medium line between 80 kilometers to 250 kilometers. And a long line when the system is bigger than 250 kilometers. So, what's a short line? Let's get a different color pen so we can distinguish between each one. Under short line, we will neglect the shunt component. So under short line, we will neglect the shunt component of the transmission line. Under a medium line, we will approximate. We'll have an approximation so we can have lumping. So this will allow lumping the shunt component. The shunt component. So under medium line, we will lump the shunt component of a transmission line. Under long transmission line, we will keep everything as it is and we will apply first and second order differential equation. We will see when we get to it. Under lossless line, we will consider R, it's equal to G, it's equal to 0. So I have no real losses into my transmission line system. Is that clear? Okay, great. So I need you to focus on these numbers, 0 to 80, 80 to 250, 200 bigger than 250, and we are going to study each one of them, and we will do an example in each one of them. Let's start with the short line. our system will be designed under 2 ports. I will define Vs represent the sending voltage, Is representing the sending current. This is 2-port network. I have receiving current and receiving voltage, and also I want to get the notation of S for sending and SR for the receiving power. So before we go any further, I need to define my system. So the notation, Vs is for the sending voltage, that's the source. Is is the sending or the source current. Ss is the sending power or the source power. I have IR is the receiving current. VR is the receiving voltage. SR is the receiving power, complex power. Okay. Let's recall, we just mentioned a short line. Now we are going to do a short line. Under the short line, if you remember, we said we neglect the shunt component. So this will be the representation of our transmission line. I have Vs, I have Is, I have IR, VR, and this is my Z of a transmission line. Now, what's an ABCD? If I want to say under this network in general, under this network, I'll have Vs, it's equal A multiplied by VR plus B IR. And I have Is, it's equal to C VR plus D IR. The A, B, C, D are complex numbers. This is very important to know. A and D are dimensionless. So A, B, C, D are usually a complex numbers. A and D are dimensionless, has no unit, so I call it per unit. B unit is ohm, C is Siemens, S unit. Is that clear? So A and D, so I have A and D are dimensionless. Let's put it in here. B unit is ohm, C unit is S, Siemens. Unit S of Siemens. So I want to apply this concept into short line. I apply almost Vs, it's equal to this voltage plus this voltage. Look, Vs, it's equal to the current, it's equal to IR Z plus VR, which is equal to VR plus Z IR. I have no shunt components, so therefore Is it's equal to IR. Based on this system, I can straight away say that A is 1, B is equal to Z, C is 0, and D is 1. I can also represent my system into matrix. I can represent my system into a matrix system by putting it this way. I have Vs, Is, it's equal to A, B, C, D, VS, VR, IR. So for a short line, I've already determined A, B, C, D for my network. For my network, I've already determined A, B, C, D by using KVL and KCL. Let's take a moment to digest this information, and we can now solve together an example. We will solve together an example. Let's great. I have an example. I have 30 kilometers line. I have a 30 kilometers line. I have the voltage, the line-to-line voltage is a three-phase system of 34.5 kilovolt. I have the line impedance is 0.19 Z. It's equal to 0.19 plus J, 0.34 ohm per kilometers. 0.34 ohm per kilometers. The system has a receiving voltage. I have, it's part of the given, V receiving. It's equal to 33 kilovolt. And I have the power receiving is, I have S of the receiving, it's equal to 10 MVA. It's 10 MVA. So, what's being given to us? 30 kilometers transmission line, three-phase, of a voltage V line to line 34.5. I have Z is 0.19 plus J 0.34 ohm per kilometer. I have the receiving voltage is 33 kilovolt. The receiving power, complex power, is 10. Question number 1. I need to find A, B, C, D of the network under consideration. Question number 2. Question number 2 is I need to find the voltage, the sending voltage. I need to find VS if the load power factor it's equal to lagging 0.9 lagging. Question number 3, I need to find VS if the load power factor is equal to 0.9 leading power factor. 0.9 leading power factor. Let's go one more time about the question that we need to solve. We have three-phase transmission line. The rating of the transmission line is 34.5 kilovolt. That's the system rating of the transmission line. I have an impedance of 0.19 plus J 0.34 ohm per kilometer. I have the receiving voltage is 33 kilovolt. The receiving S, which is the receiving complex power, is 10 MVA. Question number 1, I need to determine the A, B, C, D parameters of this transmission line. Now, this A is a short transmission line, so therefore, I already have A, B, C, D. Or I can apply normal circuit analysis to find A, B, C, D. Let's start. Question number 1. A is 1. B is Z. You have to be careful. Z is equal to 0.19 plus J 0.34 multiplied by 30. I have to multiply it by 30. If I don't multiply it by 30, everything will be wrong. C is 0, D is 1. That's how easy it was to solve question number 1. Question number 1 is done. Question number 2 is find VS if the load power factor is lagging 0.9. That's a lagging power factor of 0.9. Great. I'll write the equation. Question number 2. VS sending, it's equal to A VR plus B IR. Okay, this given to be, we found it to be 1. V receiving 33 kilovolt. That's a line to line. I always use phase in my assessment to make sure there's no mistake. So what I do now is 33, it will be converted into line to neutral voltage. So this 33 now, it will equal to 33 kilovolt divided by root 3. B is Z, which is this one. Now I need to find IR. It's easy. I have the power factor at the load, I have the voltage at the load, and I have the power at the load. Okay, let me delete this one now. Okay. I have S R is equal to root 3 VR line to line IR conjugate. So therefore, IR conjugate is equal to 10 to the 6 divided by root 3 times 33 10 to the 3. The angle is inverse of the cosine 0.9. The answer of this one will be 175.162. 175.162 angle of 25.8 degree. So IR, this is the conjugate, it's equal to 175.162 angle of minus 25.8 degrees amps. Now I found my system. Now I find my system. I found what's IR. After IR, all I have to do is apply my equation. Now I apply IR, I put IR in here, which is 175.162 angle of minus 25.8. This will give us VS line to line, VS, this VS, line to neutral. If you do the calculation, you will end up with an answer of 20.76. 20.76 angle of 3 kilovolt. VS line to line is equal to VS line to neutral time root 3 time root 3, which is equal to, the answer for me will be equal to, I multiply it by root 3, the answer will be 35.96 volt, kilovolt, and the angle will be the same, the angle of 3 degrees. Angle of 3 degrees kilovolt. No. That's under lagging power factor. I want to do now under leading power factor. This is question number 3 now. Question number 3. So for question number 2, I have VS line to line with 35.96 angle 3 degree kilovolt. That's under lagging. Under leading power factor, the only thing will change is the angle of IR angle will change in sign. So the only thing we'll do is, because now it's a leading, so the sign of the current will change, the magnitude of the current will stay the same. And I will do the same VS will be exactly the same, IA VR plus BIR. The same as before, except in here I have the magnitude of the current change, and the angle will be 33. The VS line to line, VS line to line, it's equal to 33.4 kilovolt. You end up with 33.4 kilovolt. This introduces one more element to us. I need to have, see the voltage? The system is rated at 34.5 kilovolt. Good. Then I found the ABCD, the V sending, the V source, and the leading and lagging. Same power under leading or lagging. Can you see the voltage changes? That's why the system will define a percent voltage regulation. Stuff called percent voltage regulation. Let's look on the equation of the percent voltage regulation. It's called percent voltage regulation. It's equal to V receiving no load minus V receiving full load divided by V receiving full load multiplied by 100. Multiply by 100. Now, what's the V receiving? No load. Under no load condition, under no load condition, I have IR is 0. So therefore, for my system straight away, I have VR, it's equal to VS over A. That's how VS over A. This is under no load. Because remember, VS, it's equal to AVR plus BIR. When I have this 0, I'll have VR, it's equal to VS over A. Is that clear? Let's take a moment to digest this. Did you guys digest this information? So as you can see, the voltage regulation changes whenever VS change. And as we spoke before, as a utility, I need to make sure that the load voltage is fixed. And I work backward. I have the ability to control my voltage level at a transformer, at a generator. So it's easier for me to control it this way. Now, is that clear? That's a short transmission line. That's a short transmission line system under assessment. So, before we finish this mini session, remember, we are going to do multiple sessions to cover short line, medium line, long line, lossless line, to cover the entire transmission line model. For the short line, we said we will neglect the shunt component, which means I can draw the circuit VS with a transmission line and VR IR. And based on this, I managed to find A, B, C, D parameters in respect of transmission line elements. That's why it was very important to understand the transmission line elements. After we finish this short line, we did an example and we showed how the sending voltage changes for the same power as long the power factor changed from lagging to leading. Same magnitude of power factor from lagging to leading. It will change the sending voltage. That's why every single system has a voltage regulation capability. VR, which is equal to voltage received at no load minus voltage received at full load divided by voltage received at full load times 100. And that's basically all we need to cover at this point of time for a short transmission line. Do you have any questions before we move on? Before we move on to a medium transmission line system. Let's take a moment to digest this information. Okay, I hope that was clear. Let's stop the session now and start doing a practical example together. Okay, we will now solve a couple of questions from our book regarding this element as a practice, regarding the short transmission line analysis.